We'll look at a statistics topic today of correlation, and we're going to look at an example here. You could see a very small data set where we're comparing or seeing if there's a relationship between the number of years that drivers have been driving and how much they pay per month for insurance. So you can see down here you have 5-point data set, 5 drivers, and the years that they've been driving, as well as how much they pay per month for insurance. Just off first glance, you could probably tell there's a relationship there as the years of driving goes up, but we'll take a look and I will specifically be using Desmos for all the statistical computations and graphs. Desmos is really great for that. And so on the right here, I have some practice questions for us to go over, like explanatory and response variables. What are those? And then slope and y-intercept after we create the best fit line and the equation for the least square regression line of with the least regression from all the points, correlation coefficient, and we're going to make a prediction using that equation. So lots of stuff. Let's start here with what's the explanatory and response variables. So when thinking about this question, you may think of independent and dependent variables as well. Very similar. Explanatory variables are the independent one, whereas response are dependent on the explanatory variable. So when you think about driving, how many years you've been driving, as well as the cost of insurance, ask yourself which of those do you think depends on the other. Um, Usually the problem also gives some indicator of which is the more dependent variable and which is independent by some context clues, but you can also think just from experience, right? Typically, as the number of years that you've been driving goes up, insurance is changes as a result of that. We're going to see whether it goes up or goes down. I'm sure you could guess which direction it goes, but uh, years of driving does not depend on how much you pay for insurance, right? So that if you say it out loud, you could kind of tell, okay, I can tell which one it depends on, which depends on the other. So here, the explanatory or independent variable would be years that you've been driving, because that will then determine the response or dependent variable, which would be how much your insurance costs per month. There you go. You can think of it in any other bivariate data set and in the context, say it out loud to yourself and think which depends on the other. Okay, draw a scatter plot. For this, I'm going to rely on Desmos. We can do it by hand. And by the way, when you do this by hand, explanatory variable is always at the bottom axis, and then the response is always at the top, like that, in the vertical axis, like that. But again, we'll have Desmos do this for us because it's really helpful when you have especially large data sets. So to make a list here, we click on this plus sign, and I'm going to click on table. You can call these different things if you like. Maybe I'll call this years, and then I'll call, oh, I think it doesn't like that. Okay, it wants specific annotation. Yeah, with X and Y. Or maybe like you can even say capital A and B if you'd like, but I don't think it wanted a full word. Okay, so that worked for it. So it automatically makes a scatter plot for you. You'll notice that it has this scatter plot logo image there. Um, I'll just untoggle that for now and put in my values. So if I go back to my data set, I noticed that the first values of the years of driving was from 0 to 4. So I'm just going to fill in the first part of this list with the numbers 0, 1, 2, 3, 4. And I'm looking back at the whiteboard here to see I had cost of 72 and then 70, another $70. And then it went down to 68 and 64, I believe. Let me double check. Oh, sorry, 65 and then 60. Okay, so how do we make a scatter plot? Simply toggle that back again, and you'll notice it doesn't come up anywhere here. These numbers are too small, -10 to 10, right? Both vertical and horizontal axis. So there's actually a cool zoom fit feature here. If you click on that magnifying glass, it'll take you to where those points are in blue. And I want to go ahead and capture a screenshot so that I don't have to do the drawing. I can simply paste that into our practice here. I'll just squeeze that into a smaller image. Okay. Make it fit right there. So you can't see it unless you like zoom really closely, but there's the scatter plot. You can see that it has a downward direction of the now you can more clearly see a relationship, right? But when we get to the end, we'll actually see what's the strength of that relationship. For now, I want to move on to number 3, where we compute the least square regression line equation. That means what is the best fit line that goes through these points with the least amount of distance or deviation, right, from all the other points to that line? So if I were to draw a line like this, right, that wouldn't be the best fit because we have some points that would be super far from that line. I could do better, right? Similarly, if I were to make a line like this, probably not the best fit because this is really far from the line. The other points might be relatively close. But you'll notice when we make the line in Desmos, it might do something that tries to connect all the dots in a way that creates the least distance as possible, hence the name least square regression line equation. Okay, so I'll go back to Desmos. And whenever you want that line, whatever, the only thing you have to do is similar to in algebra that you learn y equals mx plus b, but we're going to have a little variation here. So instead of equals mx plus b, we'll have y with this approximation mx plus b. And you'll notice it doesn't really do anything because I changed the name of our dependent and independent variable here of a and then b, where a, the driving experience, years of driving, was the independent variable, and b, cost of insurance, was the dependent variable. And what do you know? There's our line. If you wanted to like delete the line for any reason, you could always, again, untoggle that. But we want to see the line. So there's the line and then the equation. You replace m and b, which you may know as slope and y-intercept, with these two values in that equation. So I'm going to go ahead and write those in. I'll try to remember here. I have a slope of -2.9 and then a 73.9 for the y-intercept. All right, so y, usually, so the general form looks like this, a little bit different in statistics, but very similar concept. Y, which again stands for the insurance cost, will equal, I think I have to go back and check. The y-intercept was 73.9, and slope, very important, it was negative. So -2.9. X stood for the number of years of driving. So I like to write that down for myself, what those meant. So this was like years of driving, right? And then Y stood for the insurance cost per month. Really helpful. But this is all that the problem asks us for. And I'm going back to check 73.9. Oh, it's 73.2. So if you were thinking, hey, that's not right, you were right. I was wrong. There we go. Okay, now we want to find and interpret these two values that we got from our equation. So y-intercept always stands for what's your y value or dependent value when x, the independent value, is 0, right? So y-intercept is simply what your y, or in statistics we say the response variable's value when the explanatory value is 0. Okay, so now replace response and explanatory with years driving and insurance cost, right? So in words, this would say um, a prediction, right? Uh, a person with 0 years, just started driving experience, will pay about 73.2 per month for their car insurance per month. Okay. If you're thinking, wait, I thought we already had a value for 0 when you go back to the data here. Yes, it said that the actual person who drove 0 years paid 72 per month. And our prediction is pretty close. This is just a prediction as opposed to an actual observed value, right? So again, when you're using your equation, this is no, this is a predicted value. And whatever you get from a table or graph is the observed value. So that person who drove 0 years and paid 72 a month, that would be the actual or observed value. That comes in handy later when you learn about residual. Okay. I ran out of space, but we got the intercept, but we also need to know the slope. What does that stand for? I'll use the space on the side here. Slope is the change in your response value, right? Per unit change, per 1 unit increase in the explanatory value. So that's a lot, but it'll make sense when we actually plug in the variable meanings in here. So if we wanted to now incorporate, driving years of driving as well as the insurance cost, this means for every additional 1 year of driving experience, the slope was over here, right? That negative, again, it's important to keep the sign in there, negative 2.9. So that means the response, what was that? Insurance cost? It's changing by negative 2.9, or a negative change is the same as decreasing, right? So insurance cost decreases by not too bad, not too much, but hey, we don't complain about decrease in insurance costs. So it goes down $2.90 each month for every year that you gain in driving experience. So that's slope and intercept. Changes based on what your variables are in other problems. All right, number 5 says predict the cost of insurance for someone with 5 years of driving experience. If you go back to your raw data set, you'll notice that the data set only stopped at 4. What about for 5? How much will they pay? Well, we don't know. We don't have an observed person who drove for 5 years, but we could predict, which whenever you see that word predict, that means use your line, your linear regression. I forget already. This was 73.2 or 72.3. But use that equation for your best fit line. Oh, great. Okay. So that was correct. And think about, where does this 5 go? Does it go in for X or does it go in for Y? Again, it's really helpful that we already indicated to ourselves that X stands for the years of driving experience. So since 5 isn't year of driving experience, that tells us we plug it in for the x. So 72.3 minus $2.9 times 5. Put that in a calculator, and I'll do a quick calculation on the side. Feel free to do the same and check. 2.9 times 5 from 72.3. You get 57.8. And ask yourself, what is this? Is this a number of years or is this a dollar amount? And since this was a Y value, which stands for the insurance costs, that tells you the units should be a dollar amount per month. So that's a pretty nice decrease for someone who drove 5 years. All right, so the last question we have, what was the correlation coefficient? So that tells you how strong this scatter plot or the correlation between these two variables are. And it shows here, R stands for correlation coefficient, negative 0.939. We'll round that to 0.9. Okay, so what does that mean? If R is negative 0.9, this is a really strongly negative correlation. So you could therefore say insurance cost are strongly correlated to the years of driving experience. Right? How did I know this was a strong correlation coefficient? R works on a scale where the least it could be is -1, the most it could be is +1. Anything close to 0 is considered weak correlation. And then the extreme ends are strong. So this is a strong negative. And anything close to that, like 0.9, 0.8. And this end for R, it's only going to be values between these two, -1 and +1. That would be a strong positive, in which case that would be a graph that looks maybe more like this. But we got a graph that looked like a downward direction, right? So we can say insurance and the years of driving does have a correlation, right? Both from looking at the graph and using this correlation coefficient R. All right, so that's everything for correlation in this lesson. And feel free to, again, practice with Desmos, all these great statistical tools that Desmos offers.